All right, let's begin our look at the eyeball. The eye has on its back wall here, well around the entire thing here, a thick layer that surrounds most of the eye. It gets a little bit thinner here on the front and is transparent. We know that front layer up there in the front is the cornea of the eye. So we have the corneal covering on the front. The remainder of this out here is a white, dense connective tissue all the way around that we call the sclera. So we have the sclera and the cornea as the outermost layer. On the very front of the cornea, there's a very thin layer of epithelium continuous with that's on the inside of your eyelid. We call that the conjunctiva, or the conjunctival layer of epithelium, right on the very front in red here. Then there's this transparent cornea there, and it changes from being transparent to this white color about right here where it thickens out right here and goes around the back. So we have this thick outer sclera layer. Underneath of that here on the back of the eyeball, I have a layer in pink that represents the vascular choroid, and then a layer underneath of that that's in purple. That's the pigmented choroid. So two layers we call choroid layers there. That pigmented choroid is continuous with the mass of purple we see here. This is called the ciliary body. It's involved in focusing your lens, the ciliary body portion, and then it's also continuous with that part that forms the iris of the eye that gives your eye its color. So let's label a few parts and then we'll come back in and do a little more. All right, here we go. We've got the sclera labeled here. It comes all the way around to the cornea. Here's the cornea across here. Underneath the sclera, we have the vascular choroid in pink. It's lots of blood vessels in that. That's why it's called vascular. And then the pigmented choroid. It's a deep dark color, a deep almost black color around the back of the eye that is continuous with the ciliary body. We'll talk more about here in a minute. And the iris out here in the front. We've also labeled here the conjunctival layer, the red there that makes that thin epithelial layer over the front of the cornea. Now the ciliary body has muscle that will constrict to relax tension that's normally on the lens. This in here is the lens. Here's the lens. And attaching the lens to the ciliary body is what we call suspensory ligaments. Suspensory ligaments. So those would go all the way around the lens, and typically the lens is stretched to a certain extent. The normal state of the lens is that it's stretched just a little bit by this ciliary body. When you need to focus on something that's closer to you, we need to fatten that lens out a little bit to get the image to focus on the retina. So when we need to focus on something closer, we have muscles in the ciliary body that constrict and take tension off of the suspensory ligaments, and your lens can fatten out. As you age, the lens becomes less flexible, and when you take the tension off of it, it doesn't extend out as long or as thickly as it did when you were younger, so you have to get close-up lenses to look at the newspaper or read things up close and see fine detail. But anyway, there's your lens suspended by your suspensory ligaments, and the focusing is done by the ciliary body. I think everybody knows that the size of the pupil, and this would be the pupil opening right here. It's just a space between the inside the iris there. It's the pupil of the eye. That opening size is controlled by muscles that are in the iris. They either constrict circularly to make the pupil smaller, or there are radiating muscles that will pull the iris back out to dilate the pupil and make it larger. So we have both the circular and radial muscles in the iris. Now on the very back of the eye over here, we have in orange, this layer is the retina. It contains the sensory cells and the ganglion cells that relay information in through the optic nerve. This is the optic nerve. Right here. It goes to the brain. We'll talk more about that in a minute. So, the presence of this lens and the suspensory ligaments in here kind of separate this region of the eyeball, this big empty space here, from what seems to be empty space in the front. There's a watery fluid that occupies this front region, both in front of and behind the iris, and there's a gel-like material that occupies this space behind the lens. That space behind the lens is known as the vitreous chamber. The vitreous chamber. It contains this vitreous fluid. It's a gel-like material, kind of like jelly, like your grape jelly out of a jar, only it's completely transparent. That vitreous material inside the vitreous chamber. In front of the lens, we have an anterior chamber and a posterior chamber that contain an aqueous humor. Don't have much room to write in here, but this is the area back behind the iris. Right here is the posterior chamber. And the area then in front of the iris right here would be the anterior chamber. Both of them contain an aqueous humor. H-U-U-E-O-U-S, humor. You'll sometimes see this vitreous material referred to as a vitreous humor or vitreous gel back here. Aqueous means watery. Now a little bit of information about the retina, looking at the retina from the inside to the outside. The layer right here, this is a pigmented choroid. Back here we have a layer of rods and cones. Rods and cones layer. Those are your sensory cells right there that pick up light and convert it to a depolarization signal, which is picked up by another cell layer in here, and this is called the bipolar layer. These cells are bipolar cells. There are a couple of other cell types which relay information side to side in here as well, but the bipolar cells bridge between the layer, the rod and cone layer, and the final layer. This is the ganglion cell layer out here. Our ganglion cells have axon fibers that extend in all the way through the optic nerve to the brain. So these are the cells that send the signal to the brain, and this side over here would be your vitreous cavity, your vitreous chamber over here. So the light's coming in this way. So it seems odd that the light would have to pass through your ganglion cell layer, your bipolar layer, and through everything here before it reaches this light-sensitive part way back here next to the pigmented choroid. But that's the way it works. So your signal is first initiated here in these cells. It causes a depolarization in neurotransmitter, a change in the neurotransmitter release right here at the bipolar layer, and then those cells will release the signal then to the ganglion cell layer, and then those ganglion cells will undergo the action potential depolarization that sends that signal into the brain so we know what we're seeing. Now, as you look into the back of the eyeball, if you could look in the front and see the back retina in there, there'd be a couple of things that would be fairly obvious. There's a spot back there that looks kind of whitish in the back, a very distinct region that's slightly different color than the rest of the retinal region. And then there's another area here that's also a little bit different. A yellow color intensifies, and for that reason it's called sometimes the macula lutea. This part right here. In my illustration, I've tried to draw it with a slightly different color and a lighter spot on the very inside. The very center of this macula lutea, right in here, is referred to as the fovea centralis, or the central fovea of the retina. This other spot over here, this is called the blind spot. That blind spot is there because all of the nerves come in there, all the connections, all the nerve connections, they're coming in and they all gather up right there. And so right there where that nerve exits the eye, there are no rods and cones here. Rods and cones are absent. Over here, at this location, the cone cells become extremely concentrated. Cone cells are your color vision cells, and you have your most accurate vision in the very middle of the fovea centralis. So when you read a book, you want to put the words that you're looking at, you want to focus them directly on that fovea centralis as you scan the page. As you get away from that fovea centralis, the accuracy of your vision becomes less and less, and there become fewer cone cells. The color vision cells also decrease in number as you go away from that. So as you go this direction, you have decreasing cones for color vision, and as you move toward the outside, you have more rod cells for your black and white vision. Your rod cells are able to pick up light at lower levels than your cone cells. So when there are low light conditions, it's harder to see detail in your fovea centralis here. And as it gets darker, you make more use of the peripheral field. When it gets extremely dark, sometimes you cannot see at all in your fovea centralis. That becomes useless to you, but you can still see things out in the perimeter around that fovea centralis. You still have a little bit of light sensitivity from your rod cells out there. Now this blind spot that does not receive any signal right there, you have no vision at all right there at that point. You compensate for that inside your brain and with the help of your other eye. It just kind of fills in that blank spot for you, just kind of makes something up, more or less, for what's in that location on that incoming information. So your two eyes can work together to make up for that blind spot.